So we're going to look at section 16.3, but before that we do that, we're going to do some dissociation review. So ionic compounds will dissociate, which means that they separate, the ions separate when in solution. Okay, so you've had to do some problems like this, so we're going to look at it again. NaCl will dissociate into Na plus and Cl minus. So two particles. Okay. CaCl2 will dissociate into Ca2 plus and two chloride ions, 2Cl minus. So three particles. AlCO3, Al3 plus 3Cl minus. So four particles. Glucose is covalent. So it does not dissociate. So one particle. NH4OH dissociates ammonium hydroxide into NH4 plus OH minus. So two. Ca3PO42. So we have three Ca2 plus two phosphates. So that is five particles. Calcium nitrate. We have one calcium ion plus two nitrates. So hopefully you can see here, this is three particles. Hopefully you can see here that what I'm doing is I'm separating the ions. Okay. Oops. So hopefully that felt really clear to everybody. Okay, separating the ions. Okay, so I'm not breaking up the individual atoms, I'm separating the ions, only in the ionic compound. So this is ionic. This is covalent. This is ionic. Okay. So colligative properties. There are three colligative properties. They're vapor pressure lowering, boiling point elevation, and freezing point depression. Most properties of solutions depend on the identity of the solute. So tea versus coffee, right? The identity of the solute. What is dissolved? Okay, is it tea or is it coffee? Is it caffeine or is it sugar? Is it salt or is it mercury chloride? Is it sodium chloride or mercury chloride, right? What is dissolved? Colligative properties depend only on the number of solute particles, not their identity. Okay, number of particles. So how many? How many? Okay. So for vapor pressure lowering, okay, vapor pressure, again, is the pressure exerted by a vapor in dynamic equilibrium in a closed system, okay? So a solution that contains a non-volatile solute, so volatile is it easily evaporates, so not easily vaporizes, how about that? Okay. Always has a lower vapor pressure than that of the pure solvent. So like water, for example. Okay. So here, what we have, so that's important, right? The solution that contains a non-volatile solute, so something that's dissolved, right? Okay, always has a lower vapor pressure. So here, this has a higher vapor pressure, so it dissolves, or I'm sorry, it evaporates more easily. So in a solution, solute particles are surrounded, here are solute particles, right? They're surrounded by layers of associated shells of water of solvation, right? There are all these like slightly positive and slightly negative sides of the water, okay? The formation of these shells, and shells meaning like they're surrounding it, forming a shell around it, okay, reduces the number of solvent molecules that have enough kinetic energy to escape as vapor, okay? So this, these water, the solvent here will evaporate less or more slowly because there are solute particles due to particles in the solution. Okay, so no solute here. Okay, so that's why it's a higher vapor pressure. Lower vapor pressure because there is solute. There are particles in that solution. Okay, so here we have glucose. We have one particle. Here we have NaCl, so we have Na plus and Cl minus. We have two particles. And here we have Ca, 2 plus, and 2 Cl minus, so we have three particles. So which one has the lowest vapor pressure? So if you look back here, right, we had a pure solution, higher vapor pressure. We have solute particles, so lower vapor pressure. Okay, the solution with the most particles will have the lowest vapor pressure. Okay, so that's going to be this one, lowest. Okay. So vapor pressure lowering is directly proportional to the concentration. So when the concentration goes up, the vapor pressure goes down. Or when the concentration goes down, the vapor pressure goes up. Okay. So freezing point depression. Okay, we're going to do a lab next week where we make ice cream. When a substance freezes, particles of the solid take on an orderly pattern. We've seen this with ice, right? Presence of a solute, so this is something that's dissolved. Okay, so something, for those of you that are forgetting what solute and solvent mean. Okay, the presence of a solute disrupts the formation of this pattern, which means that more kinetic energy must be withdrawn, okay, or taken out. It must get colder in order to solidify, okay? So what happens is that the freezing point goes down. So the more solute particles in solution, okay, the freezing point goes down, or the colder a substance needs to be to freeze. So in areas where it snows, right? So Lake Tahoe, and I don't know what Lake Tahoe uses, but in Colorado, I do because I'm from there. So they put salt on the road, and they put specifically magnesium chloride. So magnesium chloride lowers the freezing point, so it doesn't ice up, the roads don't ice up. The salt, the presence of these ions lowers the freezing point. So it needs to be, even though the normal freezing point of water is 32 degrees, it needs to be much lower temperature for the roads to freeze up so that cars don't get, it's just not as treacherous or dangerous. Okay, and other times you might go somewhere and they sprinkle salt on the sidewalks, it's the same thing. So this is a little thing about how freezing depression works. Alien molecules in the water, such as ethylene glycol, okay, which is something that we'll talk a little bit more about, for example, throws a monkey wrench into the freezing process. By simply cluttering up the place, they interfere with the water molecules' ability to fall into those precise locations that are needed to form a crystal of solid ice. Okay, this is great. So it's as if a military drill team were trying to fall into formation while a mob of civilians is running around on the field. By getting in the way, the alien molecules prevent the ice crystals from growing to be as large and uniform as they would like. It's preventing that ice from forming. Even if the water does freeze, then the result will be a slush of small ice crystals rather than a single rock-hard block. Okay? So the freezing point of a solution is lower than the freezing point of the pure solvent. Okay, solvent solution versus pure solvent like water. Trucks spread a layer of salt on icy roads. Okay, this is like what I was talking about in Colorado. And different salts, they use different salts. The ice forms a solution with a lower freezing point than that of pure water. Just like what I was talking about. So the last colligative property that we talk about is boiling point elevation. Okay, so at boiling point, the vapor pressure of the liquid is equal to atmospheric pressure. So addition of a non-volatile, non-volatile means does not easily vaporize, solute, causes a lower vapor pressure, okay? The boiling point of a solution is higher than the boiling point of the pure solvent, okay? Which means that boiling point is increased. So in everybody's cars, your parents' cars, or if you have a car, you have something called ethylene glycol that was referenced earlier. And ethylene glycol does two things, okay? We call it antifreeze because it prevents the liquid in your car from freezing, but it also increases the boiling point of the water that's in your car so that it doesn't boil, okay? So it lowers the freezing point of the water and elevates the boiling point. It does both, okay? So it's helpful to prevent water. You have water in your car to prevent overheating, okay? Um, okay, to regulate. So salt isn't used and ethylene glycol is used because ethylene glycol is a better substance to use. It has a greater effect on boiling point, elevation, and freezing point depression. Okay. Okay, so the freezing point of ethylene glycol is higher than a 50-50 mix with water. And that's so that it can, no matter what the temperature gets down to, it will prevent freezing from occurring. Okay.